Last time, we explored the first law of thermodynamics, how energy is conserved in a system, neither created nor destroyed, only transferred as heat and work. But you might wonder, if energy is always conserved, why can't our engines convert 100% of heat into mechanical work? This leads us to a deeper question about the quality of energy. Although energy is never lost, it can become unavailable or degrade into forms we can't recover. This brings us to the crucial concept of reversibility. Today, we'll explore this fundamental distinction between reversible and irreversible processes and discover the Carnot cycle, the most ideal reversible process that sets the theoretical limit for all heat engines. Let's understand what makes a process reversible in thermodynamics. Let's visualize this with a piston-cylinder system. Notice how the gas particles move randomly but maintain an overall equilibrium state. In a reversible process, we change the system so slowly, like adding a tiny weight, that the system has time to adjust and remain in equilibrium at all times. Each state in this process is an equilibrium state, with the internal pressure of the gas practically equal to the external pressure from the weights. Let's review why this compression process is reversible. Notice how each state is an equilibrium state with infinitesimal changes between them. The system moves so slowly through these states that at any moment, we could reverse the process by removing weights, and the system would return through exactly the same states. This is the essence of a reversible process, the ability to retrace our path through a continuous sequence of equilibrium states. In contrast, most real-world processes are irreversible. Although energy is conserved, these processes cannot be perfectly reversed. In friction, when a block slides and stops, kinetic energy converts to thermal energy. This heat energy can never spontaneously convert back to the block's original motion. In turbulent flow, ordered fluid motion breaks into chaotic eddies, dissipating energy that cannot be recovered to restore the original flow pattern. And in heat conduction, heat flows spontaneously from hot to cold until temperatures equalize. This process never reverses on its own heat, won't spontaneously flow back to create the original temperature difference. These irreversible processes are fundamental to understanding why real heat engines can never achieve 100% efficiency. Now that we've understood the difference between reversible and irreversible processes, a natural question arises. What is the maximum efficiency a heat engine can achieve if it operates entirely through reversible processes? To answer that, we turn to an idealized thermodynamic cycle proposed by the French engineer Sadi Carnot, the Carnot cycle. It is composed entirely of reversible processes and sets the theoretical upper bound on efficiency for any heat engine. Let's dive into how it works. Let's examine how the Carnot cycle works. It consists of 4 ideal, reversible processes forming a closed loop on a PV diagram. The first step of the cycle is the reversible isothermal expansion. Let's start at point A. Let's label the temperature of the gas TH. The cylinder head is in close contact with an energy source, which we represent as a heat reservoir at temperature TH. Now the gas inside is allowed to expand. When the gas expands, it does work on the surroundings, moving the piston upward. As the gas expands, its temperature would naturally decrease, but heat is continuously transferred from our energy source back into the gas, keeping the temperature constant at TH. Because the temperature difference between our energy source and the gas never changes more than an infinitesimal amount, this is a reversible heat transfer process. The total amount of heat transferred during this step is QH. The second step is called the reversible adiabatic expansion. At this step, we remove the energy source and replace it with insulation. The system then becomes adiabatic. Adiabatic just means there is no heat transfer to or from the system to the surroundings. The gas still expands and drops in temperature. We will label the new temperature TL. In this hypothetical cycle, there is no friction between the piston and cylinder, so the process is reversible. The third step is called the reversible isothermal compression. Now the insulation is removed, and the cylinder is now in contact with an energy sink at temperature TL. In simple terms, the sink we place is at the same temperature as the gas. Now an external force pushes on the piston downward. This causes the gas to compress, and the temperature begins to rise. But as soon as it's rising, the heat is transferred to the energy sink, so the temperature of the gas remains constant at TL. Because the temperature difference between our energy sink and the gas never changes more than an infinitesimal amount, this is a reversible heat transfer process. The fourth and last step is called the reversible adiabatic compression. Now the low-energy sink is removed and insulation is placed back on the cylinder head. The gas continues to be compressed downward and it goes back to its initial state. In other words, the temperature rises from TL to TH, which means the cycle is now complete. The area inside this closed path shows us the net work done during the cycle. Keep in mind that the Carnot heat engine cycle is a reversible cycle, so every step can be reversed. We've just seen in the Carnot cycle how the system absorbs heat QH from the high-temperature reservoir and releases heat QL to the low-temperature reservoir. Now, is there a specific relationship between these two heat quantities? Could this relationship depend solely on the temperatures? Let's begin with the two isothermal parts of the Carnot cycle, one at high temperature TH, the other at low temperature TL. During an isothermal process, the internal energy of an ideal gas doesn't change because the temperature stays constant. So, by the first law of thermodynamics, in other words, the heat absorbed equals the work done by the gas. That work is given by integrating pressure over a volume change. To evaluate this, we express the pressure using the ideal gas law. Do you remember it? So for the high-temperature isothermal expansion, from point A to point B. Likewise, during the isothermal compression at temperature TL, from point C to D, the system releases heat. The negative sign here reflects that heat is leaving the system. Before we go further, take a closer look at the Carnot cycle on the pressure-volume diagram. The four processes form a closed loop, and the area enclosed by this loop represents the net work output of the engine. Why? Because the area under any curve on a PV diagram equals the work done in that process. So the total work done in the entire cycle, W net, is exactly the area inside the loop. This visual interpretation connects our heat input and output directly to mechanical work. So the area is equal to useful work. Now let's bring in the adiabatic steps of the cycle. These are the steps where no heat is transferred, but the gas still expands or compresses. They follow for the adiabatic expansion from point B to C, and the adiabatic compression from D to A, we have. These allow us to relate the volume ratios in the QH and QL expressions. Now watch this. If we take our expressions for heat and divide them by their respective temperatures, we get. But from the adiabatic relations, we know that these volume ratios are equal, so the two logarithms are equal and opposite. This leads us to a profound result. The ratio of heat to temperature for the high-temperature reservoir exactly balances the ratio for the low-temperature reservoir. This is not just a mathematical curiosity, it's a fundamental property of all reversible heat engines, and it points to a deep connection between heat flow and temperature in thermodynamic processes. This result is extremely important. It leads us directly to the concept of entropy. We define entropy change ds as the amount of heat transferred, divided by the temperature at which it happens. So, for the entire reversible Carnot cycle, the total entropy change is zero. In other words, a reversible cycle produces no net change in entropy, it's perfectly balanced. But what is entropy, really? Entropy measures how spread out or dispersed energy becomes. When we add heat to a system, we're increasing the number of ways the system's molecules can move around, and that's an increase in entropy. If you add the same amount of heat to a cold system, the energy causes a bigger change because it disrupts a more ordered state. That's why dq/T is larger when T is small. In the Carnot cycle, we absorb heat QH at high temperature TH, increasing entropy by QH/TH. We release heat QL at lower temperature TL, decreasing entropy by QL/TL. And because the process is reversible, these two changes cancel exactly. In the real world, no engine is perfectly reversible. There's always some friction, heat loss, or turbulence, and those make energy spread out even more. So in any irreversible process, the total entropy increases. Entropy tracks the irreversibility of a process. If the process is reversible, the total entropy change is zero. If it's irreversible, the total entropy must increase. Entropy gives us the direction of time and defines the limits of what we can do with energy. So far, we've seen that entropy helps us understand the limits of what's possible in energy conversion. A reversible Carnot cycle produces no net entropy, but in real-world, irreversible processes, entropy always increases. This brings us to one of the most profound principles in all of physics, the second law of thermodynamics. The first version of the second law focuses on heat engines. It states, "It is impossible to devise a cyclically operating device whose sole effect is to absorb heat from a single thermal reservoir and perform an equivalent amount of work." The second version focuses on heat transfer. It states, "It is impossible to construct a cyclically operating device whose sole effect is to transfer heat from a colder body to a hotter body." The third version is the most general and the most powerful, formulated in terms of entropy. In any cyclic process, the total entropy of the system and its surroundings either increases or remains unchanged. It never decreases. All three versions of the second law say the same thing in different ways. You can't get more than what you put in, and you'll probably get less. That missing piece, it's entropy, and it tells us not just how energy moves, but what we can never do with it.